In a recent blog post, I covered PageRank, a graph algorithm used to determine the importance of nodes in a graph. Now in this video, we will address an open question from that post. That is, how to treat for dangling nodes. I will first review what are dangling nodes, and then we will cover 3 possible methods for dealing with such nodes in PageRank. We'll cover each method in a Jupyter notebook to measure the results on an actual dataset. Now before we start, if you haven't read my original blog post on PageRank, I encourage you to review that post first before proceeding with this video. You can see a link to that blog post in the description below. So we can first ask ourselves, what are dangling nodes? So if we take a look at the example graph that we've been working through in previous blog post and previous video that I put out on this channel, we can see here that we have a simple toy graph that consists of 6 nodes. It's a directed graph, so each edge only flows in one direction. And you can see that here each node is labeled. It's labeled from A, B, C, D, E, and then ultimately F. And in this graph, we have 2 peculiar nodes. One is a pure source node, and that's F. But then we also have E, and E is a dangling node. And what do we mean by that? That is that there are no outbound links from this node. So that's simply what a dangling node is. Now, why is this an issue? Well, if we look at our definition of PageRank, we'll see that the first term here, where we sum over all the edges, is a fraction where the denominator is actually the outbound degree for the node. So we're talking about node J. In this case, the index is the connections from nodes J to node I. And so if we arrive at a node with no outbound links, we're essentially dividing this term by 0, which is not defined. Now in my previous blog post, we got around this by simply checking for any nodes with no outbound links and just simply setting this term to 0. But of course that's not correct. What's happening here is that we're losing probability mass as we iterate through PageRank. So now let's try to address this problem through 3 different techniques. And so to explore this now in more detail, let's jump into a Jupyter notebook and outline what these 3 different techniques are and experiment with them on this toy graph. Okay, so now we're in the Jupyter notebook, and we can proceed to load in all the packages that we will need for the experiments here. And now we can run the notebook that I implemented for my original blog post on PageRank. Now, if you want to work along with this example, just make sure if we hop into that notebook that the cells under verify results are all commented out. Otherwise, running the notebook won't work. So just make sure you take care of this. And now we can run the notebook, and that will also import all the objects and classes that were implemented in that notebook here. So we can already see that our edges are provided for, and here we have all the edges in the graph. We can visualize the example graph, and here it is. So here we can see that E is our dangling node, and it connects to the rest of the graph only through node D. So this is what we're going to be working with. Now just to recap what was covered in my original blog post, here we have the update rule for PageRank, and this is written in matrix notation. So the column vectors PR, these are the values of, these are the PageRank values for all the nodes in the graph at iteration T. D is the dampening factor. O hat is a modified form of the adjacency matrix. And NP is the number of nodes in the graph. And lastly, the vector 1 is just a column vector of ones, or in the case of using a personalized PageRank, this column vector will be a set of zeros and ones. So you can check out my video on personalized PageRank where I talk about this column vector a bit more. I have a link to that video in the description below. So here are the 3 different options that we will cover. I have them listed here in text. So the first one we're going to talk about is we will just record or measure the probability mass that lands at our dangling nodes, and then we will distribute that back evenly across all the nodes in the graph. So effectively, if we go back up to our visual, what we're going to do at iteration T is we first record what the current PageRank value is at E. Then we're going to take that value, divide it by the number of nodes in the graph, and add that to all the page ranks for each node in the graph. So that's option 1. Option 2 is to link the dangling node back to the node that links to it. So in our case, here we have E, and we have this single edge going from D to E. What we're going to do is add in an additional edge that goes from E back to D. So that's option 2. Finally, option 3 is to link the dangling nodes to themselves and back to the nodes that link to them. So it's slightly more complex than option 2, but in this case what we're going to do is link E back to D, and then we're going to make another edge that links E back to itself. So it's kind of like a circular edge. So these are the 3 different options. So let's dive into option 1. So here I've written out what option 1 looks like mathematically. So here we can see that this is the new update rule. And the only thing that is different between this equation and what we saw above, and that's right here, is that now we have this additional term that consists of m at iteration t, and this is the probability mass at the dangling nodes in the graph, divided by np, which is the total number of nodes. So we include this in the term, the original term on the right-hand side of the equation. That accounts for traversing the nodes in the graph, traversing them through the edges, I should say. So here we add this term, and that's it. That's all we have to do to implement this this option. So the way I'm going to do this is by creating a new class, and this class is called PageRank with Dangling Nodes, and I inherit the original PageRank class that I implemented in the original notebook. So that's the notebook that we ran up above. And the only modification we're going to do is we're going to overwrite the step function. And within the step function, I'm simply going to record the probability mass at the dangling nodes in the graph. That's what we're doing with these first 2 lines. And then when I compute the new PageRank value, and that's in P2 here, we just add the the relevant term. So that's just going to be net probability at dangling nodes divided by n. And that's it. So let's run this class, and now we can create our graph object. So if you remember, also graph is a class that I implemented in my original notebook, again, what we ran above. So we can create a graph object and now create a PageRank object as well. And now we can compute our PageRanks. So here are our values. We can make note of this and then compare these values to what we will get with the other options. Okay, so now let's go with option 2. And again, this is where we just simply add in a single new edge for each dangling node. So that's what I've implemented in the class below. This is graph with dangling nodes option 2. And here what I'm doing is I'm creating a new class that inherits from graph. And so now what we do here is in our initializer function, I simply record the dangling nodes that we have in the graph, and we add in new edges. And that's what we're doing with these 3 lines of code. And then I just call the base initializer. And that's all we have to do to implement this option. So I can run this, create a new graph object. We can see the edges inside this instance. And we can see here that where originally we had an edge going from D to E, that was it. Now we have an additional edge going from E to D. So now we can create an instance of PageRank and compute the values. So here we can see that, if we just look at the PageRank of E, it's actually quite similar to what we saw before. If we go back up here, it's 0.097, and then here it's 0.95. The obvious difference we see here is with F, which is our source node. Here it's quite low, it's 0.25, and up above it gets a higher ranking, and that makes sense given what we did with option 1. So we can already see some differences depending on how we treat for the dangling nodes. But again, let's keep note of this and just proceed on with option 3. So as I mentioned before, now with option 3, we're going to implement 2 new edges for every single dangling node. And I'm going to proceed in a similar way as to what we did for option 2. So here I'm going to write a new class, graph with dangling nodes option 3, and this inherits from the original graph object. And here again, like before, I detect the dangling nodes that are present in the graph, and then now I add in the new edges. And now it's just an edge going from the dangling node back to itself, and an edge going from the dangling node back to the node that links to it. So that's what we're doing here, and then I just call the initializer from the base class. So we can run this, we can declare an instance of graph, we can view the edges, and here we can verify that now we have an edge going from E to E, and we also have one going from E to D. So we can compute the PageRanks, and we can see our results. Now I tabulated all the results here, so it's a lot easier to compare. And what we see here is in the first column, I have all the nodes in our graph labeled, and then I have the PageRank results from the original PageRank. So this is what we did previously in my original blog post. We have options 1, 2, and 3 that we covered here in this video. And now I'm also going to compare it with the PageRank that comes out of the box from Scikit Network. So we can compare all these different PageRank techniques together. And what we see is that with scikit network, the dangling node gets a much higher rating than any of the options that I tested out here. In fact, the approach that comes closest would be option 3. So the values for the dangling node E is most similar there. Also for F, A, and B, it's fairly similar. We see that there's some differences between the rest of the nodes. C, not so much, but D, we see that there's a big deviation as well. But I don't know the details for how PageRank was implemented in scikit network. But we can see here that, yeah, just using different approaches to dealing with dangling nodes can produce different results. So ultimately, the choice will have to be up to you. You have to see what makes the most sense for the project that you're working on, which approach should you take. Another thing to consider is that we haven't touched on any of the hyperparameter tuning, so we just kept the dampening factor at 0.85. Now, if we change this value, it will certainly change the results that we get and how different the results are from each of the options. So that's another interesting thing to point out. Also, the complexity of the graphs themselves will have some effect. So how many nodes and how many edges connect those nodes in the graph will also have an impact on the sets of values that you can expect to get from whatever approach is implemented for PageRank. So that's also something to consider. So that concludes this video. I hope you enjoyed this and got some value from it. If you did, please like, share, and subscribe to the channel. That's always appreciated. I have a link to this notebook as well. I always post the code that I work through on my GitHub, so you can download this and experiment with it for yourself. Yeah, and I hope you have a great day and see you in the next video.